In this session, I am going to discuss the module 4, that is a context-free and non-context-free languages, as a session 3 of 18 CS 54. So here I am going to be discuss further the topic context-free and context-sensitive languages. At the outset, we are going to be discuss the design of the Turing machines, the principles behind to design the Turing machine for the particular problems, as we constructed the various state diagrams, or it may be through the transition diagram, or it may be a transition table, or it may be a instantaneous descriptions. The various mechanisms we have discussed in the earlier case, those we are going to be devise here, employ here for the particular problems. So the design criteria we have seen in length, and the allied problems we are going to be solved for the particular problems. So this is a part of the presentation. The milestones going to be in subsequent slides, especially related to the design of the Turing machine concept. So before going to be say about this concept, so we have normally see that how this Turing machine concept evolved. So related to the finite automata, for example, A star, that regular languages will be accepted by this finite automata. So that is the foundation laid down, and based on that, the subsequent language is going to be evolved, especially context-free languages. So that is a power n and b power n. So normally this is going to be accepted and certified by the non-deterministic push-down automata concepts. So those concepts are well established, and normally to help for this context-free language recognition, and with their respective grammar for particular applications. After discussing this, the regular language and context-free language, so we have the Turing machine concept. For example, A power n and b power n and c power n, that is a string w, and can concatenate with one more string the w along with that Turing machine concepts. So we're going to discuss in length in this session. So that is the design of the Turing machines, that is. So here we can see that the design criteria, the basic guidelines for designing a Turing machine. So that we have seen three mechanisms, that descriptions, or diagram, or table. See, the fundamental, the prime objective in scanning, examining a symbol, that is a input symbol, which is placed on the infinite length tape. That tape is comprises the n number of cells. Each cell is going to be accommodate the particular character, and that is going to be pointed by the read out head. It is know that what to do in the future. So that will be read write head will be a guide, that is finite control will be it is the scanning the pointer, which is going to be placed over particular character, and read write for operation will be performed, and the Turing machine guide will be tell that to move towards left side or right side. The Turing machine must remember the past symbol scans, the not only current symbols, the previous symbols also is going to be play a role here, for which that Turing machine must remember the past symbol need to be scanned, that is. So that is the criteria that Turing machine have small amount of memory. So in that memory, it can go to be record that past symbols. So that past symbol might also it help here to move forward. The Turing machine can remember this by going to be a next unique states. So next unique states, the state which is going to be occupied in the subsequent step. So that may be a very unique, rare state will be there. So in that case, that could be, it has to be remember the previous information, how it came from the came to that particular state right now. It came from the previous state, so that previous state should be recorded that. So number of states must be minimized. So the number of states must be minimized that. So this kind of the number of states will be provided for the particular machine is going to be represents that the computational aspects in case of memory or in case of the time. Ultimately this is going to be yield the particular cost of the algorithm. So the particular cost of the algorithms, which will be more detailed, you might have studied in detailed analysis of algorithms. There either maybe a prior analysis or a posterior analysis. The prior analysis, we have seen that asymptotic notations with help of the omega or with maybe theta, and the so on. The notations are maybe best case, worst case, and average case. Timing aspects we have through that, and also you can profile the algorithms as a part of the posterior analysis of an algorithm. So that could be help used to how much computational aspects will be exaggerated or involved or going to be evolved here. So those all aspects will be coming in a picture, and the more number of states will be there, and obviously so that is going to be higher rate of the computational aspects. So in which case in that respect, the number of states which going to be represented by the Turing machine, which is going to be optimized one, it should be minimized one, so that we can bargain with the amount of resource which will be required at the computational point at the personal computer, or that going to be simulated with help of this Turing machines model. This model is going to be always bargain with this how to minimize this the optimize the resource. They may be in terms of the number of states, and in terms of the number of cells, in terms of the length of the tape, and with respect to the Turing machine concepts. So that is going to be more detail about is essential. This can be achieved by changing the states only when there is a change in written symbol, or when there is a change in the movement of the read and write. So this can be either possible, either writing a symbol into the particular cell, or the read write head, that finite control will move towards the left side or right side. That movement is also going to be cost. See, the writing an information into the cell is also cost. Reading an information from the particular cell of the tape is also cost. So these are all the responsible to yield or contributes something to amount of the amount of effort is required to bring out the solution for the particular problems. So this kind of that Turing machine going to be sensitized to this minimization of the or optimization of the resource in terms of the states, or in terms of writing the information to the cell, or in terms of the moving ahead to the left and right. So these are all the effort which will be essential to required. So that is going to be reduced to the possible extent. So we shall explain this with help of the example in the subsequent slide. So that going to be more elaborative, and it would be quite interesting. So it would be going to be appreciate the design philosophy of the particular Turing machine which we are intended to solve. So let's take an example of design the Turing machine recognize all the strings consist of even number of ones. The example, the Turing machine we need to be designed with that machine should accept a string which consists of even number of ones. Even number of ones, there may be 0 ones or 2 ones or so on, that is. So even number of ones going to be inputted to the particular Turing machine, it going to be accept after the every even numbers which going to be considered, who is going to be read, or who is going to be examine that cells which is exist in that particular tape. So solution here, the construction is made by defining a moves in the following way. So let's consider the Q1 is an initial state. Q1 is an initial state with a start notation that machine enters into Q2 on scanning 1 and writes B. Right. So initially at Q1, the machine at pointing at the state Q1. So that is going to be initial state. By the various notations we can identify that it is an initial state. So contains the single circle, and the left side there is a pointer will be there. So that is always the standard notations will be followed in most of the topic which you discussed in the deterministic finite automata so far. So the Q1 is the initial state, and that particular machine enters into the other state called Q2 from one state to the other state after consuming the input 1. After consuming the input 1, or after examining the input 1 from the tape of the cell, after testing that is a 1, and writes the B. That is a B is the input symbol of the tape. Input symbol of the tape is a part of the Turing machine. The write the blank at particular after reading writing. So you need to be scan them by the potentiality to bring out the scanning the results, which can be replaced by the B or some other characters, right? So normally the B is going to be more important here, going to be a place, that is, if M is in a state Q2, if M is in a state Q2 and further scans 1, it enters to Q and writes B, right? Further scans 1 and writes to, because even number of ones will be there, so if it is a 1, then it will be right and it will be finished, that is. If the next one, if M is in a state Q2, that is earlier Q1 to Q2, now it is a Q2 that scans 1 and enters to Q and writes the B. So that is the second one. The C step, that is a third step here in this the solution which is going to be provide for to design a Turing machine for recognize to even number of ones, that Q1 is only accepting a state. Q1 is accepting. So M accept the string if it is exhaust all the inputs, symbols, and finally is in the state Q1. Q1 is only accepting state. And also initial state. So Q1 have a dual role here in this the problem going to be evolved for this purpose, that Q1 is going to be initial as well as the final state, initial as well as the accepting state, initial as well as the halting state. So M accept the strings if it is exhaust all the input symbols. M accept the strings. So n number of ones it accept. So that is exhaustively all the input symbols are accept. So it reaches to the Q1 state, wherever it may be, it come back to the Q1 state. So finally is in state Q1. Finally is it in the state Q1. The exhaustive all the inputs in the sense that n number of inputs, n is equal to 0, n is equal to 2, n is equal to 4, so on. That is even numbers going to be considered for the n case. So symbolically we can have that is going to be considered. So the consider that is M is equal to Q1 comma Q2, that is 1 comma B, and n1 comma B delta, that is a transition function. Q is a final state which participate in the big Q, a blank B is a blank, and Q1 is going to be final state. So Q final state, that is going to be emerge, that is. So here the this design we can express through the help of the transition table or transition table, that is a present state. Q1 will be there. After accepting 1, then it will be 1 will be replaced by B, that is a blank, and it changes the state to Q2, and the finite control that read and write head will move towards the right side to go for is there other ones will be there, the next ones will be available there. So Q1 to Q2, and 1 will be read and 1 will be replaced by the blank, and it go to the Q2, and the tape moving towards the right side, right? To tape moving towards the right side, in the sense that it understood there is a still number of ones will be exist. So next from the Q2 is a present state, then it will be read the same one, because the even number of ones are their input. After reading one, it may be replace the blank, and coming back to the Q1 state, and tape will be moved towards the right side. So this will be happen for even number of times. Let us obtain the computation. Let us obtain the computation sequence of 1 1. So thus that is a Q1 1 1. So Q1 1 1 is an input here. Beginning a machine at the Q1 and input is a 1 1. So this symbol, that is a instantaneous description. The instantaneous description. So after reading 1, it going to be replaced with a B, that is a blank, and the machine will be changed state to the Q2, right? So B Q2 and the 1 which is unread symbol. So now at this junction, so after with the help of the notation called instantaneous description, B Q2 1, B Q2 1. So now again exercise this instantaneous description. So we have the B Q2 1, then this 1 is going to be replaced with a blank, and it coming back to Q1. So the next one which is there, so this is going to be scanned or examined. After examining, understood that is a 1, then replace with the B. So there is a 2 B's will coming, and the machine will go to the Q1. So machine will go to Q1. As Q1 is an accepting state, so 1 1 is accepted. So 1 1 is accepted. So from this the transition table and with help of this instantaneous descriptions going to be denote how this machine will be traversed towards the right side. Especially in this case, the going to be read the number of ones. Going to be read the number of ones, that is a even number of ones going to be going to read here. So from this problem we can see that the other possibility. So not acceptable case. This is a case we examine for even number of ones, that is n is equal to 2 ones. Let me see exercise the same problem for odd number of ones. So odd number of ones, what will happen? It should not be accept. It should not be accept. So how you can see how it will be performed? Let me see that Q1 it is a 111, that is a odd number of ones is given, and with help of the notation called instantaneous description, the after reading the first one we will replace with the B, right? Then machine go to the Q2, and still 1 1s are there. So that one, the next one we are going to be read. So after reading that the second one will be replaced with the blank. That blank Q1 will be there. Then still 1 is there. So that one also we are going to be read with the help of the instantaneous description. That is the blank 3 blank, due to that the previous 3 ones. All the 3 ones have read and scanned and examined. We understood that is a 1. That's why we replaced with a blank. And now it reached to the Q2. Now it reached to the Q2. So due to that odd number of ones, so M machine model, that is a Turing machine model, going to be hard at Q2, right? Q2 is not an accepting state. Q2 is not an accepting state. It, of course, it is an intermediate state. So the no Turing machine, the no DFA will stop at intermediate states. If it start at intermediate state, it will be catastrophe. It will be hanging. It will be struck in this there. So it will not going to be yield the proper results. So Q2 is not an accepting state at all. So that's why the input 1 1 1 is not an accepted by the machine which you design for even number of ones. What we have given, the odd number of ones we have given, that way it is a failure. So it will accept the strings only even number of ones. That is a philosophy. That is the inference we have to draw from this the solution which is provided for designing the number of ones, that is. So let me move further. So design a Turing machine that will be over 1, B, which can compute the compute a concatenation function over L is equal to 1 bracket L is equal to set, that is open bracket 1 close bracket. If a pair of ports W1 and W2 is an input, the pair of words strings we are going to be input, that is W1 and W2, the output has to be W1 and W2. So input is a W1 comma W2, the output is a concatenated version of the W1 and W2. those they padded one they padded or attached to one after the other, especially in that order W1 and W2, not W2 and W1. So in that fashion, that Turing machine should be able to calculate the inputted string, that is two string, and emerging string will be single string of having double length. So that is the philosophy behind to provide a solution for this. So let me proceed how it will be happening. So let us assume that the two words W1, W2 are written initially on the input tape separated by the symbol B. So symbol B, that is a blank. If example you can consider here. So if W1 is equal to 1 1, W2 is equal to 1 1 1, 3 ones, that is. W1 is equal to 2 ones and W1 is equal to W2 is equal to 3 ones. Then input and output of the tapes are as follows, that is. So here you can consider, so we have W1 1 1 and that will be separated by the blank, and W2 will be 3 ones and again it will be padded with the blank. On either side the padded with the blank, that is the architecture of the tape. So that is the nature of the tape which could be considered, and output should be 1 1 1 1 1, 5 ones. This blank is as shifted to the last, that is towards the right side. So we have the string is arrived at the concatenated. This is an input and this is the output they expecting. So here observe that main task is to remove symbol B. So main task here we have to remove the symbol B. So this can be done in the subsequent way. So the separating the symbol B is found and replaced by 1. Separating the symbol B is found. Separating the symbol B means we need to identify the symbol B and replace by the 1. So with help of the finite control, that is a reader and head, that has to be scanned and go by examine cell by cell. It goes to that particular character where that blank is exist. Once is found, then it we have to replace by the 1, right? So that is the initial way. The next we can have rightmost one is found and replaced by the blank B. So after replacing the one with a blank, and the rightmost one we need to be cancelled. We need to be cancelled, right? We need to be place the blank so that it is not examinable, or it will be blank. It is a null kind of thing, or it is not concerned to that cell, is not concerned to us, because that compensated by the cell which is present in between of the W and W2 which we have placed in the tape, right? So read write head returns to the starting position. So after rightmost read write head reach the rightmost position, there we have replaced the blank by 1, and read write head returns to the starting position. So the we have that instantaneous description. So Q0 11B 111, the instantaneous description 1 Q what is that? Okay, well Q0 1B 111 instantaneous description 11 Q2 B 111 instantaneous description 111. Where that blank was there, that we replaced with the 1, and Q1 will be there. So the after that 3 ones will be there. So now that last 3 ones we have to read, that is after reading the 1 then we have to move forward without replacing any character, and move to the next last character where we have 1, then that 1 will be replaced with a blank. So we will have, that is a 5 ones Q2 1B. So that we have 4 ones that is a Q3 1BB, and triple ones Q3 1B, and instantaneous description that 11 Q3 triple one blank that double B, and 1 Q3 triple 4 1 double B. So these are all the effort they are doing to returns the read write heads that returns to the starting position. So where it begins at the Q0 here. So till that point it moving towards the left side, that pointer, that is similarly Q3 came here, So Q3 is there, and that finally that blank will be replaced. That is, so it generates the concatenated string which going to be emerge here as a result. The computation for 11B11, the computation for 11 blank 111 from the computation sequence of the input string 11 blank 11, right? So computation, we can construct the transition table for the input string 1 blank 1 blank 1, right? So here we can see that the present state and tape symbols are 1 and blank, no 0 here. That vocabulary of input have only one, that B is a default from the tape side, so that is a 1 comma B, that is. So Q naught it will be read the first one, that is a 1, and move towards the right side and remain in the same state, right? So when it is a blank, it replace with a 1, and move towards the right side and change the state. When blank occurs, it replace by 1 and move towards the right and change the state, whereas it will read 1 and it no replacing 1 will be remain as it is. Tape will be read write head will move towards the right side and remain in the same state. So when it occur blank, in that case it will replace 1 and also change the state and keep moving right side. So that is observation we are doing demonstrating here for the accepting the string 1 blank 1. So when we go to the next state, that Q1, it would be read the 1, then go to the remain in the same state, it will be to move towards the right side because the few more characters are there to go be examined. So now we can observe that the blank will be appear, that if the blank will be appear, then we can keep that blank and turn towards the left side and change the state, that is a Q2. So that kind of mechanism will be happening, that Q2 when 1 will be there, we have to replace with a blank, then move towards the left side, then to come towards the initial state, that is a point behind that moving towards the left side, change the Q to Q3, and from Q3 then 1 is input, then it go to the 1 LQ3, that is moving towards the left side. In the case of blank, then blank will be replaced with the blank itself, move towards the right side, then it will be Q1. So that Q1 or QF is a final state going to be reached, that is going to be the computation sequence is given as, that is Q1 1B1 instantaneous description 1 Q2 B1. From this table only can elaborate this. 1Q B1 instantaneous description 11Q, that blank will be replaced with the 11 Q1, and further the 111 Q1B, that is a blank will be there 11 Q2B. Then we can have, that is a concept, that is going to be discussed, that is 1 Q3 11 BB, that is going to be discussed, that is Q3 11 BB, and that is the instantaneous description Q3B 11B, that the reach to the final state, that is a B Q final state 11 blank blank, that is a 11 blank blank, that is going to be read, that is. So further we can see that the one more problem. So design of the Turing machine. So design of the Turing machine to recognize the language 1 power n, 2 power n, 3 power n, where n is greater than or equal to 1, right? So design Turing machine to recognize the string which is 1 1, it depends upon the n, 1 power n, 2 power n, 3 power n. So before designing the required Turing machine model, let us evolve the procedures for processing the input strings. Consider the input strings where n is equal to 2. If n is equal to 2 means 2 ones, 2 twos and 2 threes, right? So when n is equal to 2, then 2 ones, two twos and two threes. So that is one case. After processing, we required an instantaneous description to be formed, right? So the formation of this instantaneous description, so as follows here. So blank blank blank, so there is a 6 characters are there, so there are 6 blanks assumed here. So at q1 to q1 to q7, so the processing is done by using the 5 steps. So following 5 steps going to be substantiate or witness for the designing this problem. The first step is Q1 is the initial state, right? Q1 is initial. The read write head scans the leftmost one. Read write scan heads the leftmost one, that is. So that going to be consider here, that is move to right side. So replace 1 by B and moves towards the right, and M enters to Q2. M enters to Q2. So after scanning this, it 1 by B, it go to be enters to the Q state. On scanning the leftmost two, the read write head replaces 2 by blank B and moves towards the right side. So M enters to the Q3 state. So on scanning the leftmost three, so that is leftmost 3. So read write head replaced by B and moves to the R. M enters to Q4. So after scanning the rightmost 3, so the read write head so moves to the left side until it finds the leftmost one. So it keep going, that is. So as a result, the leftmost 1, 2, 3 are replaced by the blank. So in that case, we can have blank 1, blank 2, blank 3 kind of intermediate results we can observe, that is. These 5 steps are especially 1 to 4 are repeat, all the 1s, 2s, 3s are replaced by the blanks. So we have understood from that step the first 1s, first 2s, first 3s are replaced by the blank. You can repeat for this 4 steps for n times. If n consider the finite value, so the change of instant description due to the processing 1, 1, 2, 2, 3, 3 is given as. So let's consider that through the instantaneous description, Q initial state Q1 and 1, 1, 2, 2, 3, 3 is the input we want to test for the design of the testing machine, Turing machine. So the ID. So 1 will be replaced by the blank and move to the Q2. Remaining will be there, and next B1 will be scanned out and go to the 2. So 2 will be replaced with the blank, and next going to be read 3. So similarly 3 going to be replaced with the blank. So B1, B2, B3. So by the time we can have B1, B2, B3. So once that reaches the leftmost last symbol, which is 3, and it start moving towards the that is B1, B2, Q5, B3. So that B1, B, Q5 to B3. So that is a B1, Q5, B, B2, 3. That is a blank will be coming here. So once after scanning the all symbols one iteration, and the tape will be moving towards the left side to come at the initial state, and again go for the next iteration. So that is happening for here. So Q6, B1, B2, B3. So next Q1, 1, B2, B3. So on that is. So that is a triple B, 4B, Q3, B3 will be there, and here we can consider this triple B, 5B, Q3, 3, and will be that go to the Q4 and will be replaced, and total all B's, that is all 6 character will be replaced by the blank, and it will be there at the final state Q7. Hence it is coming to initial state, that is accepting state 1, 1, 2, 2, 3, 3, that is a Q7, and all blanks after consuming the finite number of instantaneous description. After exercising the finite number of instantaneous description, we may able to get an output that is Q7, that is a 6 blanks. 6 blank was the 6 character was inputted there. So as a Q7 is an accepting state, the input string is 1 1 2 2 3 3 is accepted. Now we can construct the transition table respectively. So the present state, the input symbol is what are those input symbol? 1 2 3 and blank. So vocabulary, that is sigma is equal to 1 2 3, blank, blank is from the tape symbol side. So we have Q1. So after reading the first symbol A, that is replace with a blank and move towards the right side and change the state. When you similarly when you read the 2, read the 3, so on, that is when is a blank is there, blank will be undisturbed, keep the blank as it is, then move towards the right side and go to the change the state Q1. So now at Q2, when you are at Q2, we maybe read the 1, then if you read the 1, you undisturbed, that is keep as it is there and it remain the same state. When you read the 2, then replace with the blank, as we did in the previous case here when you read 1. So now we are reading 2. So then when you are reading 2, then you replace with the blank and move towards the right side and change the state, right? Change the state. So similarly blank is there, we have to be there itself and change the state, that Q2. So coming to the Q3, right? Q3, the Q3 1 is not necessary consider, 2 is consider, then remain undisturbed, the 2 keep as it is, because we have to read the 3, right? So now we have to read the 3. After reading 3, then replace the blank B in the place of 3 and move towards the right side and change the state called Q4. Right, change the state called Q4. So that is a B or Q, that is as it is. When B blank occur, then the move towards the right side, then remain state will be changed, that Q3. So now we are at the Q4. That means that all the ones we have read, first 1 2 3 those were read now. So now we are at the Q4 state. So when you are Q4 state, that is a 3 will be there. When you read the 3, then you have to 3 will be there. Don't disturb that 3. Then keep as it 3. Then move towards the left side. That is, so move towards the left side. That is, we can have, so BL blank, that is Q7, that is, so blank 7, that is we will have, that is, so Q5, that is 1L Q3, 1L Q3. So 2L Q3, that we have to keep as it is. When that is a blank will be there. So at we have Q6, 1 will be there, then towards the left side. When you blank, then move towards the initial state called Q1, then will be remain there. It can be seen from the table that strings other than those of the form 1 power n and 2 power n and 3 power n are not accepted. So this is designed for only 1 power n, 2 power n, 3 power n, not for 1 power n minus 1 or 2 power n or 3 power n plus 1. So there should be an equal number of 1s and 2s, 3s will be there in the given input. So only such inputs going to be accepted from this Turing machine through this transition table and the instantaneous description, which are enough evidence to help us to understand this concept. So it is advisable to compute the computation sequence of the string like 1 2 2 3, 1 1 2 3, 1 1 2 3 3, and then see that these strings are rejected definitely, because the non-uniform distribution of the all 1s 2s 3s, right? So there should be uniform distribution of 1s 2 3s should be only acceptable. So these strings are not acceptable from this Turing machine, which you have seen from 1 to steps 1 to 4, and final step is going to be conclude to declare the acceptance or rejectance, which we have also witnessed through this transition table. So further, that is a transition function going to be discussed, that is the delta functions will be there. So from that Cartesian product of the q and lambda, that going to be tape symbol going to be considered the current state. So input symbol, that resulting state, the tape symbol replacing input symbol, and movement of the read write head or left or right. So we can call this the formal description of the Turing machine. Just we have machine language and higher level language for the computer. So we can have that higher level description called the implementation, and this movement of the head symbol store etc. That English example, single instruction like move to right till end of the input change requires several moves. So further that single instruction can be implemented through the several moves of the standard Turing machine. So the higher level we can give instructions in the English language even without telling that transition function. So this is called high level description implementation. We have seen that is. So from the prescribed textbooks, Ilan Rich, Automata, Computability and Complexity, the Pearson Education, and that book contributing more towards to narrate the most of the examples, and especially that Misra and Chandrasekharan, the computer theory of computer science, the Prentishala of India publications is a good book, which is most of the material is borrowed from the book. And of course the additional reference are there, that is Hopcroft, Motwan and Ullman. Those are the automata, the introduction to automata theory and languages are going to be also the helpful. Michael Sipser, introduction to theory of computation, the additional support for most of the literature. John C. Martin, introduction to literature, language and the theory of computation. So Tata McGraw third editions is also the auxiliary, the data auxiliary input for this discussion of the design of Turing machines. We have gone through this concept. Thank you for patient listening of the topic, that design of machine and the related problem we have solved, and once again we have recapitulated that discussion with Turing machine. So I hope you followed the concept. Thank you for patient hearing, and also thanks for the coordinator and moderator and the subject expert. Once again, thank you to all. Thank you.